Let's wait for others to join the class. Okay. Please ask your friends to join the class. We'll lock the meeting after 5 minutes. Today we'll see the two topics. First we'll study the work energy method, then unit load method. Okay. I'm sharing my screen. Let me know if it is visible or not. Okay. Are you able to see the screen?
Calculating displacements in structures using energy methods. Part 1, Work Energy Principle. Energy methods, such as the method of virtual load, have been widely used for calculating deflections in trusses, beams, and frames. In this lecture, I will provide an introduction to energy methods by discussing the work energy principle in the context of simple structures.
Audio and video is okay?
In essence, the work energy principle
Okay.
states that work done by forces
So we'll start after 1 minute. CR, please ask everyone to join the class. My voice is audible. My voice is audible. Okay. Okay. So let's start today's class. Please go through this topic, energy methods. Okay. Work energy principle.
Calculating displacements in structures using energy methods. Part 1, Work Energy Principle. Energy methods, such as the method of virtual load, have been widely used for calculating deflections in trusses, beams, and frames. In this lecture, I will provide an introduction to energy methods by discussing the work energy principle in the context of simple structures. In essence, the work energy principle states that work done by forces acting on an isolated system, such as a structure, equals to the change in the system's internal energy. What does that mean exactly? And how is this relevant to structural analysis? Let's start by defining work. From physics, we know that work equals force times distance. More specifically, if a force F causes an object to move a distance d in the direction of the force, then work done by F is F times d. The above definition assumes that the object is free to move. When it comes to stable structures where rigid body movement is not permitted, the system is not free to move. Therefore, the above definition needs to be altered a bit. Let's see how much work takes place when a vertical force is applied to a beam. Suppose we have a simply supported beam to be subjected to a concentrated load at the midspan like this. But let's apply the load incrementally. At each increment, we are going to add a small amount of load to the beam. I'm going to denote this small load increment by symbol F. Say at time t0 there is no load on the beam. At time t1, we are going to place the load F on the beam. Consequently, the beam is going to displace a small amount which I refer to as delta. Obviously, what you see here in this diagram is an exaggerated displaced shape of the beam done for illustration purposes. In reality, since load F is very small, delta is negligible. Nevertheless, at time t1, a small amount of work has been done by F as the force goes through displacement delta. The work done here is F delta. Let us tabulate the results so far. At time t0, the applied load is 0 and so is the work done. At time t1, the applied load is F. The displacement is delta and the work done is F delta. So now let's place the next load increment on the beam. Here it is. At time t2, a second F is added to the beam, causing an additional delta displacement. How much work do you believe has been done at this step? I am not looking for the total work at the end of the second step. Rather, I want to know the work increment done at t2. To figure out the answer, we need to ask the following questions. How much displacement takes place in this step? And how much force travels through that displacement? The displacement increment at this step is delta, right? That is, for every F, the beam displaces by delta. And since the load increment here is F, so is the displacement increment. But how much force goes through this displacement at T2? Examine the diagram. How many F's do you see? 2. That is, 2 F's travel through delta. Therefore, at time t2, the work increment done is 2F delta. So, let's update our table. At t2, total load is 2F, total displacement is 2 delta, and the incremental work done is 2F delta. Now, we are here at the third step. We need to add another F to the beam. This causes the beam to displace an additional delta. So, what is the incremental work done at T3? The incremental displacement is delta, and 3 F's travel through it. So, the work increment at this step is 3F delta. Here's the data in tabular form. Hopefully, you can see the emerging pattern. At time T4, total load on the beam is 4F, Total displacement is 4 delta, and the incremental work done is 4F delta. We continue incrementing the load until the entire intended load is applied to the beam. Say that happens at time step n. So at Tn, total load is Nf.
Till here understood that at time t0 the load will be 0, displacement will be 0, and your work will be 0. At time t1, Hanjar, mute yourself please. Hanjar, please mute yourself. Rule number 77, mute yourself. Am I audible? My voice is okay.
Yes, madam.
Okay. So see at time t1 your load was F, so displacement you get delta, and your work was F into delta. Okay. Who is talk? Mute yourself now. All of you mute yourself. What is this guy doing? Okay. So at t3, your load is 3f, displacement is 3 delta, and the work is 3f delta. Like that, there will be number of times, n times. Your load will be n into f, displacement will be n into delta, and your work will be n into f into delta. Okay. So let's continue.
Total displacement is N delta, and the work increment is Nf delta. What is the total work done by the applied load? The sum of the work increments. Although we can determine the external work by calculating the sum, there's an easier way to do this. Let's graph our tabulated data.
So if I place a load versus displacement curve, I'll get a straight line. Okay.
We get a straight line. That is, the relationship between load and displacement
And this applicable for your linear elastic material.
is linear. This is so because we're dealing with linear elastic material. The work done by the total load simply is the area under the line graph. This is the area of the triangle with height NF and base N delta. Since NF is the total applied load, let's call it P, and N delta is the total displacement under the load. Let's refer to it as big delta. Then external work equals to 1/2 P delta.
So if you see this figure, it representing a triangle. Okay. So how to find the area of a triangle? Half. It will be half base into height. Okay. So half base, this base and the height, they are taking the deflection. Displacement is represented by this delta. Okay. And this base is represented by the load. So area of this triangle will be half base into height, which is half p into displacement, and this is known as your external work.
Before we proceed further, let's visualize external work in a few problems. Here, the work done by P is 1/2 P delta. Here, the total work done by the applied loads is 1/2 P1 delta 1 plus P2 delta 2. Similarly, Here we can write work as 1/2 P delta.
Please mute yourself. Why you unmute yourself?
And here work is 1/2 P delta. For this beam, work can be written in terms of the product of the applied moment by the rotation of the beam under the moment. So external work here equals 1/2 m times theta. And here, total work is 1/2 m times theta 1 plus m times theta 2. Now let's turn our attention to internal energy. What is it, and how do we calculate it? Energy is stored work. Where is the work generated by the load stored? In the member. When we apply the load to the beam, when the beam bends, we are producing work and storing it in the beam as internal energy. When the load is removed, the energy converts back into work, forcing the member to unbend. When a load is applied to a structure, its parts or elements are deformed. Consequently, internal forces develop in each element. The work done by the external load is propagated through the structure and stored in the elements as internal energy. The energy stored in each element equals 1/2 its deformation times its internal force. Let me elaborate. In this beam, external work done is 1/2 2 delta. The beam can be viewed as many infinitesimal elements, each having a deformation like this, and each element is subjected to an internal moment like this. For example, if we take the infinitesimal element located at point A, then we have something like this. Here, the internal moment in the beam is 3 kilonewton meters, and d theta A denotes the amount of rotation of A. So the internal energy stored in this element is 1/2 3 times d theta A. The total internal energy is the sum of the energies stored in the individual elements. For our beam, this can be written as, therefore, for this beam, the work energy principle can be written as, I will come back to this example later.
So here your external work will be equal to internal energy. Now they have related this work with the energy. Okay. Who is speaking? Ivan, mute yourself. Okay. So your external work is half 2 delta and your internal energy half m d theta, and equating from 0 to 10 the distance. Okay. With the
When
boundary
we are ready
conditions.
to actually perform the integration at the right-hand side of this equation. But for now, let's focus on simpler problems that help us develop a better conceptual understanding of the work energy principle. Consider a straight bar of length L subjected to an axial force of P. The load causes the bar to elongate. Let's refer to this elongation as delta. Then, the external work done by P is 1/2 P delta. According to the work energy principle, the external work has to be equal to the internal energy stored in the bar. In this example, the structure consists of one member only. The internal energy stored in the member equals.
So as per this work energy theorem, your external work whatever the work is done externally is equal to the internal energy of that member. Okay, the strain energy stored in that member will be equal to the external work done by that member.
1/2 of the internal force in the member
And internal
times
energy
its
is member force into member elongation divided by 2.
elongation. So, we need to find the force in the member and the member's elongation. Using a simple force analysis, we can determine the internal force in the member. The member force, denoted by N, has the same magnitude as P. This force causes the member to elongate. Let's refer to this elongation as small delta. The internal energy stored in the member is 1/2 N times delta. But how to determine delta? We use the relationship between stress and strain for this. Since we've assumed linear elastic material behavior, Hooke's law applies. That is, axial stress in the member equals to the
As per Hooke's law, your stress is directly proportional to the strain, right? Now this stress is your axial stress and strain is your axial strain, okay? And E is your Young's modulus of elasticity.
material's modulus of elasticity times the member's axial strain. Since axial stress equals N over A and axial strain equals delta over L, we can write, or delta equals NL over EA. Then the member's internal energy can be written as, since N equals P, we get internal energy equals 1/2 times P squared L over EA. Since external work equals internal energy, we can write. So there you have it, the work energy principle in algebraic form. Other than showing the relationship between work and energy, does this equation have any use? The answer is yes. We can use it to solve for the system displacement under the load. We can use the equation to solve for delta. But this was a really trivial example. How does this principle work if the structure consists of multiple members? Since you asked, let's look at a less trivial example. Consider this triangular truss structure. Under the applied load, the truss deforms like this. The total external work equals 1/2 P delta. Let's find delta using the work energy principle. The structure consists of 3 members. We need to find the internal
So this theorem also applies to your truss and also to frames also, okay?
energy stored in each member. To do so, we need to know the internal force in the member as well as its elongation. Since the truss is determinate, the member forces can be determined using the method of joints. And, as before, the member elongations can be determined using Hooke's law. Here are the member forces in terms of P.
So by the method of joints we have discussed in earlier classes, right? From that method you can find the various sources in the members all the members, right? You can find all the forces in these members. So they have just showed the how to find, just briefly explain. They briefly showed the member forces in various members. These are the member forces.
Here is the
So
elongation of member
you can
AB.
use these member forces to find out the internal energy and external forces.
Here is the elongation of member AC.
They are using the Hooke's law.
Here is the elongation of member BC. Then, the total internal energy stored in the truss equals
At last, all the member forces.
Equating the external work to the internal energy, we get
Equate this internal energy with the external
now
force,
solve for
which is
delta.
half P delta. So your delta will be 9 by
So
4 PL
now
E.
we know a thing or two about formulating external work and internal energy expressions for trusses, and how to use the work energy principle to calculate truss deflections.
So hope everyone understood this part. We'll have the next part of this. My voice is okay? Okay. Okay. So we'll have the next part in after some time, means after 2-3 minutes. So that was about the work energy principle theorem. Okay, it can be applied in your truss, beams, and frames, different frames also. So for the time being, I'll consider this one as first class. So give me the attendance of this class in the chat box, please. Write your roll numbers in the chat box. Anyone left to write their roll number? Their roll number? Okay, I'll put a message in the group, then join the class, okay? You can leave the meeting, after some time we can join. I'll text in the group. Jantadan!